Swayam Prabha. Digital India. Educated India.
Hello everybody, welcome to today's lecture on material balance calculations for single units with multiple reactions. In the last few lectures we have performed some example problems where we did material balances for reactive processes. In those systems we had only a single reaction taking part inside the reactor. Here we are going to look at reactions which are happening either in parallel or in series and try to use the same principles which we learnt and the terminologies associated with multiple reactions to solve for the flow rates and conversions. Let us start with the first example problem. Methane is burnt with air in a continuous steady state combustion reactor to yield a mixture of carbon monoxide, carbon dioxide and water. The reactions which are taking place are given as methane plus oxygen forming carbon monoxide and water and methane plus oxygen forming carbon dioxide and water. The feed to the reactor contains 7.8% methane, 19.4% oxygen and 72.8% nitrogen. The percentage conversion of methane is 90% and the gas leaving the reactor contains 8 moles of carbon dioxide per mole of carbon monoxide. You are asked to calculate the molar composition of the product stream using both molecular species balances and atomic species balances. Let us now try to solve this problem. If you look at the problem, you see that no flow rates have been given. So we can use a convenient number as the basis. So here I have assumed a basis of 100 moles of feed, as we have the mole percentages for the feed stream which is coming in. We can calculate the composition of the feed stream as 7.8 moles of methane, 19.4 moles of oxygen and 72.8 moles of nitrogen entering the reactor, where 90% of methane is converted to form product stream which contains unreacted methane and oxygen and also contains carbon dioxide, carbon monoxide, water vapor and nitrogen leaving the system. It has also been given that the ratio of carbon dioxide to carbon monoxide is 8 moles is to 1 mole. So this is the selectivity for the reaction. So now that we have the selectivity and the composition of the feed stream and also the conversion, let us try to perform material balance calculations to get the number of moles of each of the component in the product stream and then calculate the molar composition of the product stream. So the problem requires us to perform both molecular species balances and atomic species balances. Let us first start with the molecular species balance. So the molecular species balances can be written as follows. You have input minus output plus generation minus consumption equals accumulation. For non-reactive components, generation and consumption would go to 0 and at steady state accumulation would go to 0. So let us start with nitrogen. So in case of nitrogen, it is a non-reactive component. So generation and consumption will be 0. At steady state accumulation will also be equal to 0, giving you input equals output. So the input moles of nitrogen is known as 72.8 moles of nitrogen. So based on that, N2, which is the number of moles leaving through the product stream, would also be equal to 72.8 moles. So this gives you the first information. Now we can write the balance equations for the other components. Let us start with methane balance. So methane balance would be again input minus output plus generation minus consumption equals accumulation. No accumulation at steady state. Methane is a reactant, which means there is no generation of methane. So the equation for output is input minus consumption. Input is already known, so we just need to calculate the consumption. So methane can technically be consumed by both the reactions. So reactions 1 and 2 both consume methane, and it has been told that the total consumption of methane is 90%, which is the conversion of methane. So total consumption for methane would be 0.9 times input, which is 0.9 times 7.8 moles, giving you a total consumption of 7.02 moles. So thereby we can calculate the output, which is NCH4, as 7.8 minus 7.02, giving you 0.78 moles of methane leaving the system. So we have now calculated the number of moles of nitrogen and methane. Let us start writing the balance for carbon monoxide. CO balance, again input minus output plus generation minus consumption equals accumulation. So carbon monoxide is a product, which means there is no consumption and there is only generation. At steady state there is no accumulation also. So your output term becomes input plus generation. So as carbon monoxide is not entering the system also, output is actually equal to only generation. So to calculate generation of carbon monoxide, we need to know how much of methane is entering into the first reaction and how much of methane is actually entering into the second reaction. So let us call consumption of methane by the first reaction as CH4 So generation of carbon monoxide, generation of carbon monoxide would be equal to consumption of methane in reaction 1 based on stoichiometry. So this generation term for carbon monoxide is equal to consumption of methane in the first reaction. Similarly, for carbon dioxide, the generation term for carbon dioxide would be equal to the consumption of methane in the second reaction. Now we already know that the total consumption of methane is 7.02 moles, which means consumption of methane in the first reaction plus consumption of methane in the second reaction is equal to 7.02 moles. So substituting the generation terms for carbon monoxide and carbon dioxide there, we would have GCO plus GCO2, which are the generation terms, is equal to 7.02. So this can be equation 1. Another information which has been given to us is the ratio of carbon dioxide and carbon monoxide in the output streams, which is NCO2 divided by NCO is equal to 8. So we already know from the balance equations that the number of carbon dioxide moles leaving the system would be equal to the amount of carbon dioxide generated, and similarly number of carbon monoxide moles leaving would be equal to the number of carbon monoxide moles that are generated. So substituting the generation terms here again, we would have GCO2 divided by GCO would be equal to 8, giving you an equation GCO2 equals 8 GCO. So this is the second equation. Now that we have two equations and two unknowns, we can solve for the number of moles of carbon dioxide and carbon monoxide that is generated, which will also be equal to the number of moles of carbon monoxide and carbon dioxide that is actually leaving the system. By solving these two equations, we get NCO2. We get NCO2, which is equal to generation of CO2 as 6.24 moles, and NCO, which is equal to generation of carbon monoxide, again which is equal to 0.78 moles. So this gives us the information about the carbon monoxide and carbon dioxide leaving the system. So now we have calculated the number of moles of methane leaving the system, number of moles of carbon monoxide leaving the system, number of moles of carbon dioxide leaving the system, and number of moles of nitrogen leaving the system. We still need to calculate the number of moles of water and oxygen which are leaving the system. So let us write a balance for water. We start again with input minus output plus generation minus consumption equals accumulation. So no accumulation at steady state. Water is a product, so which means there is no consumption. There is also water not entering the reactor, which means your generation is equal to your output. However, in this case water is generated by both the reactions. So, your total output which you get would be equal to generation from reaction 1 plus generation from reaction 2. So, how do we calculate the generations for each of these reactions? From the stoichiometry, we know that for every mole of CO generated in reaction 1, 2 moles of water is generated. Similarly, for every mole of CO2 generated in reaction 2, you have 2 moles of water generated. Therefore, you know that 0.78 moles of CO generated implies that you have 2 times 0.78 moles of water generated by reaction 1 and 6.24 moles of CO2 generated by reaction 2 implies 2 times 6.24 moles of water generated by reaction 2. So, the total output would be equal to the generation of these two terms, which is 2 times 0.78 plus 2 times 6.24, giving you a value of 14.04 moles. So, this would be the number of moles of water present in the product stream. So, we still need to calculate the number of moles of oxygen leaving the stream. So, let us write the oxygen balance. Start with input minus output plus generation minus consumption equals accumulation. Oxygen being a reactant is not generated, it does not accumulate under steady state conditions, giving you input minus output minus consumption equals 0. So, your output is equal to input minus consumption. Oxygen is consumed in both the reactions. So, consumption in reaction 1 would be what? So, we know that for every mole of carbon dioxide produced, you have 2 moles of oxygen which is consumed. From the stoichiometry, you know that for every mole of carbon dioxide produced, you have 2 moles of oxygen consumed, and for every mole of carbon monoxide consumed, you have 1.5 moles of oxygen which is consumed. So, using that, we can calculate the consumption of oxygen in the first reaction as 1.5 times the generation of carbon monoxide, which would be 1.5 times 0.78 moles, and consumption of oxygen in the second reaction would be equal to 2 times the generation of carbon dioxide, which is 2 times 6.24 moles. So, the total output of oxygen would be input, which is 19.4 moles of oxygen minus 1.5 times 0.78, which is the consumption from reaction 1, minus 2 times 6.24, which is the consumption by reaction 2, giving you the final output as NO2 equals 5.75 moles. With that, we have all the components which are present in the product stream. We know the moles of each of these components. The summation of all these moles will give us the total moles of the system. Using that, we can calculate the product composition. So, the product composition would be 0.78% methane, 5.7% oxygen, 72.5% nitrogen, 0.78% carbon monoxide, 6.2% carbon dioxide, and 14% water vapor. So, this is the product composition given in terms of molar percentages. This is how we would go about solving this problem using molar species balances. Now, let us see if we can solve the same problem using atomic species balance, and let us compare the answers and see whether we get the same answers. You can also try to see which of the techniques is simpler for you and try to adopt one of these techniques for your calculations. Now that we are considering atomic species balances, we need to understand that generation and consumption terms go to 0. atoms cannot be created or destroyed. So, generation and consumption are 0. At steady state, accumulation is also equal to 0. So, all atomic species balances we would have would follow the form input equals output. Let us start writing the atomic species balances for nitrogen. So, nitrogen balance would be 2 atoms of nitrogen entering with each molecule of N2, thereby giving an input of 2 times 72.8, and the output would also be 2 times NN2, because you have 2 atoms of nitrogen leaving in the form of nitrogen molecules. So, your NN2 is equal to 72.8 moles. So, now we can write a carbon balance. When we write a carbon balance, we need to know how much carbon is entering, which is in the form of methane. So, you have 7.8 moles of carbon entering, and there is only one atom of carbon in methane. So, 7.8 times 1 is equal to number of atoms of carbon which is leaving the system would be 0.78 times 1 in the form of methane. So, we know this because we have 90% conversion of methane. So, thereby only 0.78 moles of methane is leaving the system, and we have 1 atom of carbon in carbon dioxide and 1 atom of carbon in carbon monoxide. So, we write it as 1 times NCO plus 1 times NCO2. So, this gives us an equation of NCO plus NCO2 is equal to 7.02. So, we already know that NCO2 divided by NCO is equal to 8. This information has been given in terms of the selectivity. So, using that and the first equation, we can calculate NCO and NCO2 as 0.78 moles and 6.24 moles. So, this gives us the moles of carbon dioxide and carbon monoxide in the product stream. We can now write the balance equations for hydrogen and oxygen to perform these calculations. Hydrogen balance, we have 4 atoms of hydrogen entering per molecule of methane. So, atomic balance for hydrogen would be 7.48 times 4, which is input, is equal to 0.78 times 4, which is the number of atoms of hydrogen leaving through methane, plus NH2O times 2. So, using this we can calculate NH2O as 14.04 moles, and finally we can write the oxygen balance, which would be 2 atoms of oxygen per molecule of oxygen entering, which is 19.4 times 2 is equal to 0.78 times 1, which is the number of moles of carbon monoxide which is leaving the system, plus 2 times the number of moles of carbon dioxide leaving the system, which is 6.24, plus 1 times the number of moles of water vapor leaving the system, which is 1 times 14.04, plus 2 times number of molecules of oxygen leaving the system, giving you NO2 equals 5.75 moles. So, again we have been able to calculate all the terms which we have looked for. So, if you were to compare the values which we got through molecular species balance and atomic species balance, they would all be the same, validating that the techniques we used and the final answers we arrived are accurate. So, we can again calculate the molar percentages using these values to get the same values as we got using molecular species balance. So, with that we will come to the conclusion for today's lecture. We will continue with more example problems where reactions happen in parallel and series for us to get more clarity on how to solve such problems. Thank you.